Okay, so I thank FSS for organizing this very nice workshop. I'll use FSS quite often in this talk. Yeah, so this will be based on joint works, several works with my students, some of them unpublished. Yeah, so this audience doesn't need introduction to PIT, but anyways, I'll do it. And then we'll discuss ABPs, ROABP, which you have already seen in the previous talk, and the new ideas and some conjectures. So PIT question is, the general question is for general arithmetic circuits, which means the degree may be exponential in the size, whether it is 0. And yeah, so ideally we want the algorithm to be polynomial in the size, these many bit operations. So since we talk about bit operations and time, you can assume the field to be just standard, either finite field or Q. Okay, you don't have to worry about function fields or other fancy stuff, p-adics. You don't care about that. So brute force expansion will be as expensive as S to the S, no more than that. So these many field operations, you can certainly solve this question. And using randomization, you can even solve in polynomial in S time. Okay, that's the famous Schwarz-Zippel-Demilo-Lipton algorithm. So it's basically just that increase your field size slightly bigger than the degree of the circuit, syntactic degree or whatever, actual degree of the circuit polynomial, and then just pick a random point from that whole big space. Okay, so it has been rediscovered many times. So this test has the advantage that it is black box.
Sorry, do you want to say something about the 1922?
Yes, so actually this was mentioned to be by one of my PhD students in Bonn, by Johannes. So he found this out from some comment in some blog of Lipton. So Ore, yeah, he already uses something like Schwarz-Zippel in one of his proofs, and he doesn't care to, give a proof or give it a name.
Is it the OR for OR rings in the non-commutative?
I don't know anything more. So, but online you can look for this and you can find that exact theorem on the proof where he's using it, and you can see that it is some primitive version of Schwarz-Zippel, without mentioning. Yeah. Yeah, sure. No, already in I think classical proofs of this NNL type theorems, Newton normalization. So in algebraic geometry, basically when they say generic, a generic point, that for us is just a random point. And they don't care about Schwarz-Zippel or proving these things. Generic just means that. So in that sense, but anyways, yeah, so just for completeness, why not also Ore when we have 4 people? Yeah, so this algorithm is black box, so it is very strong. All it needs is actually merely a degree bound, not even the circuit size. Okay, the circuit is required simply to compute the polynomial at the given point. But all the theorem needs is just what is the degree bound. And but yeah, for as an intermediate step before finding a black box PIT algorithm, you can ask. You can assume that the circuit is given to you explicitly. You can look at the gates, the constants on the wires, everything. So that is the version of white box version of PIT. So in this talk, we will be interested only in the black box version, and that is actually equivalent. So if you cannot see the circuit, then all you can do is you have some pre-processing algorithm after which you have computed a set of points, and no matter what circuit is, you will just evaluate the circuit on all these points. Okay, so that is called the hitting set. It has to be small, and it's each of the points, the description should also be small. Okay, for efficiency reasons. And the property it should have is that in your family, any circuit, non-zero circuit from your family should have a non-root in this set. Okay, and note that when the field is rationals, then actually the number of such circuits is infinite. So these infinitely many circuits in your family, which is, let's say, size S, your finite small set H should also always have a non-root. Now it is actually easy to see that easy to prove that these sets exist. Okay, the difficulty is finding an efficient algorithm. It should be explicit. That is the open question. So question of interest for us is design hitting sets for, in this talk, very special circuits. As a general motivation, this appears, so my motivation is just because it's an algebraic question, natural question, but it also appears in many places in computation. So there are complexity results like IP equal to P space theorem, and then finally PCP theorem, coding theory, and in algorithms it appears in many places. So this graph matching, for example, so tomorrow Rohit will talk about bipartite matching. So there PIT appears, symbolic determinant PIT appears for the same reason in matrix completion, equivalence of branching programs, interpolation, primality testing, learning of circuits, polynomial solvability. There are equivalences of PIT with factoring due to Amir and others. And also in algebraic independence tests, finally PIT is what is used. So PIT has real applications as well as theoretical applications. Hitting sets, moreover, are of interest because they are related to circuit lower bounds. So you must have already seen these trade-offs. That, for example, the question of separating permanent from determinant or VP connects to designing strong enough hitting sets. Not just any hitting set, but there are specific theorems that specific hitting sets would give you a proof that a polynomial is hard. Okay, so there are several results of this type. So philosophically, it's this thing that the hardness question flips to algorithmic question. And yeah, so this is a good thing because you can now focus on finding efficient algorithms, hopefully find strong enough tools to understand what does a circuit do. Okay, once you know what a circuit does, what a circuit is, you can also, they should be, obviously the tool should be useful also in proving lower bounds. And on the first day of this workshop, you must have had a good enough dose of GCT vis-a-vis PIT and hitting sets. Okay, so that is another connection. So that is the general motivation. Any questions here? Okay, so then I'll move to the more specific models. So in this talk, I'll be working with a special case of ABP. So ABP are special circuits. They are especially useful for low degree polynomial computation. Okay, so circuits in general of sizes due to repeated squaring, you keep multiplying the same thing again and again s times, so you can reach a polynomial of degree 2 to the s. Okay, so when you are not interested in such high degree polynomials, when you only care about polynomials of degree polynomial in n or polynomial in s, okay, then ABP is a more natural model. Right now it is supposed to be weaker than low degree circuits, but if you believe Ramprasad's conjecture, then low degree circuits should just be the same as ABP. Okay, so either way, his conjecture may be true or false, but either way ABP is a very important model. Okay. Yeah, so now you can actually quote this, call it the SC, Saptarishi's conjecture. But it's also related to your SC, right? Yeah, this is just, yeah, so there are two ways, at least two ways to define ABP. One was what Arpita said. the graph definition. The other which I prefer is here is the iterated matrix multiplication method, where you basically you have these so without loss of generality, you can assume that you have symbolic matrices, D matrices. So symbolic means that every entry is either a variable or a constant. Okay, and you multiply them out, and let us say again without loss of generality, we look at the top left entry. That is a polynomial. So that is the polynomial which I say has an ABP. Okay, so that is the ABP representation of a single polynomial. Whether you can express it as an entry in a matrix product, everything should be only moderately large. So the parameters here are, if the matrices are W by W matrices, that is the width, that is called the width, and this D here is called the length or the depth of the ABP. Okay, so width and depth, n variables. So fx is said to have an ABP of this much width and depth. And ABP is quite important because there are these famous theorems that, first of all, ABP is equivalent to symbolic determinant computation model. Also, constant width ABPs are very interesting. So, constant width ABP is equivalent to width 3 ABP is equivalent to formulas. Okay. And moreover, width 2 ABPs, they are already almost equivalent to depth 3 circuits. And at least at the level of PIT, these two problems are the same. Okay, polynomial time equivalent. And which obviously makes width 2 very interesting because you have the depth 3 Qasm, right? So just even there are even more special properties. So width 2 ABP, where you restrict the matrices to upper triangular, already this is this captures depth 3 PIT. Yes.
But the width 2 cannot you cannot write every polynomial as a width 2 ABP, right? Can you? Because that's a paper by Elena and Deng that says width 3 is long.
Right. So yeah. So this is up to a PIT. So you can write any sigma by sigma representation up to a product by linear, by basically not the same, maybe not the same polynomial, but f times a product of linear polynomials can be expressed as a width 2 ABP. So you have to introduce us a kind of a multiple which will have a width 2. So yeah, it's not exact representation, but up to PIT certainly polytime equivalent. And even width 2 upper triangular. Okay, so this is the minimum level of non-commutativity that you can introduce. So here the matrix product is in general non-commutative. You can also assume, you can also look at the restriction where the matrix product is commutative. That is also an interesting open model, but yeah, so certainly if you reduce the width and just add a little bit of non-commutative product, you capture the Qasm, depth 3 circuit Qasm.
What do you mean by captures? What is capture? PIT.
No, here it is stronger. This is width 2 PIT is polytime equivalent to depth 3 circuit PIT. It is polytime equivalent, so.
I don't know what is. So you mean if there is this, then there
Yes.
But this is it can be vacuous because if, for instance, there is nothing. What do you mean? It's an algorithm that transforms this.
Yes, they are polytime equivalent. So if you find any algorithm, well, it is actually a many-to-one reduction. So I can reduce any sigma by sigma instance to a width 2 ABP instance. It's a many-to-one reduction, not even sorry.
If you have a reading set for one, you have a reading set for two.
Whatever, white box, PIT, black box,
White box.
anything. Any other questions? Okay, so that is about ABP. We are interested in this talk in ROABPs, which seem very special. So here what we assume is that these matrices are univariate polynomials. Okay. So there is some known or unknown permutation on the variables x1 to xn, and if you look at these individual factor matrices, they are just univariate polynomials in xi, by which we mean that now it's a W by W matrix where the entries are univariate polynomials over the field. Okay, so as Arpita pointed out, this equivalently you can see it as just a univariate polynomial over the matrix algebra. Okay, that is what these are. And there is then some degree bound of the so individual degree you can assume to be d. So you have width W, depth or length n, individual degree d. So total degree is at most dn. Again, low degree regime. Yeah, so in the black box, in the white box, obviously order is known. In the black box, order is unknown. But there is also a gray box model where the order is known, but the details are not known. Okay, so you can study any of these. Why is this model interesting? So, well, this is a natural restriction of ABP. Yeah, it is also, first of all, it is inspired by ROABPs, which Parikshit talked about. So read once branching programs in the Boolean word. It is clearly inspired by that. And in algebraic complexity, there are other models which interestingly reduce to this case. Okay, so two such models are set multilinear depth 3, which was introduced by Amir and Ran, and diagonal depth 3. Sorry? By who? Oh, I thought in Raj Pilka you, but it was already available before that. So yeah, these are natural cases of ROABP. Actually, diagonal depth 3 will reduce even to commutative ROABP, so where the matrix product commutes, and set multilinear is known only to the non-commutative version. Okay, so diagonal is supposed to be even, the simplest model, which is kind of open and reduces to ROABP. So what are these? Just for completeness, again, I'll give you the definition. So a sigma pi sigma circuit is this sum of product of linear polynomials. Okay, depth 3 over some field. And it is called set multilinear when it is multilinear. So, okay, what does multilinear mean? Multilinear means that every product gate here computes a multilinear polynomial. So that means Lij's for a fixed I, Lij's are, as you vary j, they have disjoint variables. Okay, so since the variables are disjoint in the ith product gate, it actually induces a partition on the variables. Okay, every product gate corresponds, induces a partition. Now we call it set multilinear if all the partitions are the same. Okay, so C is called set multilinear if there is a partition P that is common for across I's, across the product gates.
I know this is probably a dumb question, but in the Boolean world, this would be, I think this would be like oblivious read ones, because the order is
Yeah. So this is read once oblivious. Yeah, there is a word. So if you drop the word oblivious, then we cannot write. We may not be able to write that object in this. No. So I mean, you can only say that it is an iterated matrix product with the special property that whenever you look at a path, it's read once. No. So yeah, these things, there are some partial results due to Amir and Mike and many others recently. Yeah, so some of the methods do generalize to that scale, but it certainly becomes harder. And yeah, some of the methods here so could be relevant beyond just read once oblivious. Okay. So yeah, so this is set multilinear, and For this, due to Amir and Ran, there is already a white box polytime PIT. And it is not just for set multilinear, but actually it generalizes all the way to ROABP. Okay, but you have to have all the details of the ROABP. It is not gray box. It's really white box. And the other model diagonal, which is even simpler, is that for a fixed, for any I, all these Lij's, they are essentially the same. Okay, so you have product gates being just a power gate. Okay, all the project. So you have a sum of power of linear polynomials, and maybe their linear combination. So each product gate is a dth power. The degrees may even be different. So this for this also. So basically, what was done is that this can, by something called a duality lemma, it can be re-expressed as an ROABP, and then for ROABP you have a white box PIT results. So the same algorithm. So, any questions? Okay, so this is the basic motivation for ROABP, and what is known. So I'll quickly go through the ideas. It seems to be a fertile model. So already this white box PIT algorithm is quite interesting, and you already saw the characterization of ROABP due to Nissan in the previous talk. So that that notion of rank of any arbitrary, of any polynomial over a field, which Arpita talked about, that is also called eval dimension. And so whenever eval dimension of a polynomial with respect to some variable order is small, then there is also a low width, small width ROABP. Okay, it's an exact characterization, and Arpita showed you how this can be done also algorithmically. Okay, so using okay, it is not really necessary for the white box PIT algorithm, but yeah, that is something even older than this result. And recently there has been attempts to solve black box PIT for this model. Okay, this is still an open question, but there have been several ideas, some of which you must have already seen last week. So what the best they give is quasi-poly, and quasi is not very bad, so it is like n to the log. Okay, n to the log sized hitting sets. And so the last result in here was this AGKS. So if the width is, if you are looking at width W individual degree D n variate ROABP, then size raised to log of n time hitting set. Okay, so in the exponent, the log that appears only acts on the number of variables. Okay, that is the final result, the best amongst these. And yeah, so the ideas here are okay. I'll very quickly go through this idea. Probably it won't help you at all, but anyways, maybe it will give you the keywords. So, so the idea is to find a monomial ordering. So what is a monomial ordering? Monomial ordering just sends a variable to xi is sent to t to the some weight. Okay, so you want to discover a phi which will send xi to t to the some weight. So basically in particular it will send any monomial to the dot product, right? And so sorry, this is t now, and yeah, so now this number is associated with all these exponentially many monomials, and you get some kind of a ordering, right? So you can say that this monomial is smaller than the other monomial if this number is smaller than the other monomial in the image. Okay, so try to find a monomial ordering on the monomials. with the property that given an ROABP, you try to isolate a least basis. Okay, so your monomial ordering should, in some sense, so basically, if you multiply this out and then look at it as a polynomial over the matrix algebra of constants, the coefficients are not simply field elements since they are matrices. So they overall span a subspace which is at most dimension W square, right? So you can talk about at most W square sized basis, and you want to now order these coefficients in a way so that a least basis appears in a unique way. This is what isolation is referring to, that you can isolate that. So the advantage would be that I mean, if you can find a map where the WIs are only, let's say, polycized or quasi-polycized, then n variables will be reduced to a single variable. Okay, so this will give you an algorithm. This will become a hitting set. So the way it is constructed, the way we construct it is recursively. So we look at variables x1, x2, x3, x4, x5, x6, and yeah, so we reduce n variables to n by 2 variables. So this is very similar to what Parikshit described as Nissan's idea in the Boolean word. So pairwise you reduce the variables. N variables will be reduced to n by 2 variables, and so on. And then ultimately you can make it univariate, so you will actually be able to reduce n variables to a single variable and get a hitting set. Yeah, so this may not give you much information, but it can be expanded. So that gives you a hitting set, which means that the corresponding polynomial f corresponding to this D, which is a matrix. So D is a matrix, and the polynomial, you'll get a polynomial if you multiply it from the left and on the right. So here by a row vector, constant, let's say constant row vector, and here by a constant column vector. So this will then become a polynomial. And for this, you will get a hitting set in the end. Okay, so if this was a non-zero polynomial, it will remain non-zero under this univariate substitution. That's a hitting set. But actually, this least basis isolation is a stronger. It has a stronger property. It has this property that if you shift this D by it, right? So now you are looking at n plus 1 variables. This has low support rank concentration. Okay. In general, I don't know how to prove that hitting sets give you low support rank concentration, but this map which we construct is actually stronger. It satisfies this low support rank concentration property, which I think you have already seen. What it means is that now, if you just focus on, in this case, log W support part of this D prime, shifted D, then already there the coefficient span is equal to the whole coefficient span. Okay, so the rank gets concentrated in a very low part. This is the strongest result which we get in this paper. Well, not really in this paper, but yeah, by the methods of this paper. So the bottom line is that non-zeroness of ROABP can be pushed to low support. Okay, that is kind of a strong property of ROABPs. Any questions? So that is one of the last ideas in this long sequence of work. And yeah, so now this basic model ROABP, these techniques can be used as a building block for slightly more general models. So this first result is what you saw in the last talk, given by Arpita, that if you now look at a sum of a few ROABPs, so in the hard case they will all have very different orders of the variables. Okay, so this you don't expect to write it as a small single ROABP. Okay, in fact there are results by Neeraj and Chandan that even sum of two ROABPs cannot be written as a single ROABP, small ROABP. So yeah, these are inherently different from ROABPs, but somehow you can reduce the PIT question to several ROABP PIT questions, okay, as happened in the last talk. Ultimately,
How does this compare to read key times?
it's a special case, very special case.
Depends on what you mean by also read K. There's like different definitions. If you have, it's like, suppose you have a read-once pricing program, right, and you have an order. It could be that you're reading the variable order in the same order each time, or you could have different orders each time. Right? So if you have the same order each time, it's basically the same thing as reading it once.
Hmm.
If you change
Yeah.
the order, then you can simulate this model.
If you have the same order each time, it's the same as just read once.
I mean, you load the width goes from W to W to the K.
Okay.
I don't know if that's obvious.
But general read K ABP is far more general than this, right?
Yeah.
So, yes. Yes, but yeah, these techniques here, they have been used by Mike in studying read K ABPs as well, PIT and lower bounds. So here the exponent is slightly heavier. So first of all, the log on the number of variables now becomes log on everything, W and D. And second thing is that dependence on K in the exponent is exponential. But for constant K, yeah, it's still quasi-poly. Yes, and this proof is again, as was suggested in the end of the last talk, this proof again is based on rank concentration and it also gives rank concentration. Okay, so the proof ultimately shows that sum of few ROABPs after a shift also has this property. The support parameter in the rank concentration is now simply this exponent. Okay, it's log support, but dependence on K is exponential. And the white box result here is just as good as, it's basically an extension of Rasch-Pilka. Okay, so there is no log in the exponent, the dependence is only on K, constant K, this is polytime. Yes, and this is, when I say hitting set or black box here without any qualification, it means that this is really black box. So no knowledge is needed. Orders are arbitrary, unknown, and yes, only the parameters are known. That's all. So the idea here is, as was apparent from the last talk, that you try to answer the question about two ROABPs, whether ROABP A is equal to ROABP B, and you try to write the polynomial B in the order of the variables in the ROABP of A. Okay, you rewrite, you basically try to construct an ROABP for B in terms of the one that exists for A, using the interdependencies of coefficients, polynomial coefficients given by A. So all that can be done. Basically, it's a combination of rank concentration ideas and evaluation dimension ideas. So you get white box and black box. And yeah, so ultimately you have to do several ROABP PITs in this. And the other model where ROABP is used is multilinear depth 3 model, for which exponential lower bounds are known. due to the other Amir and Ran. So PIT was only brute force, but then using ROABP ideas and other projection ideas, it is slightly less than brute force. Okay, so here n to the 2/3 essentially. So the idea here is you consider various projections of the circuit and somehow try to reduce to several ROABP questions. But this is very vague. I mean, the proof is much more complicated. I don't think I understand the proof completely. Yeah, maybe. So any questions? Okay, so that is the old stuff in ROABP. So the new stuff is so the new result is that we will now look at a different restriction, which is constant width ROABP. Okay, so if there was no RO, if it was just constant width ABP, that we know is almost a general question even for width 2. But when you look at read once oblivious, then it becomes a much more restricted model. And maybe we can do this in polynomial time, the hitting set I mean. So that is what we will show, that for constant width ROABPs, we give a really poly time black box PIT. So the idea emerges from a map which is already very interesting in the bivariate case. Okay, so we look at just A1 times A2, this matrix product, and get a map which will be degree insensitive. Okay, that is the key property. So what is a bivariate ROABP? Well, it's a bivariate polynomial which can be written as A1 times A2. Okay, and then there is a row vector, a column vector, which are constant vectors. W ambient space is W dimensional. And we don't talk about the degree of A1, A2. The degree can be arbitrary. Okay, and so what this means simply is that F has this type of a representation. Okay, so F is a sum of W products. The factors are univariate, arbitrary degree. And yeah, so this is just a rephrasal of this eval dimension versus ROABP characterization of Nissan. So if you look at the coefficient matrix of this polynomial F, so what is that? This is a matrix where the entries are, so you index the rows by x1 monomials and columns by the remaining, which is x2 monomials, right? And the coefficient of x1 to the I, x2 to the j in F is then a constant. So put that constant in this place. Okay, so it's a constant matrix, and its rank, you can see that eval dimension essentially means rank of this matrix. So this is exactly min width. Okay, so this is at most the current width, which is W. That's the characterization. And so now you look at the action of this map. Okay, this is our new map, which sends x1 to t to the width. T is a formal variable. So x1 is sent to t to the W, and x2 is sent to this thing plus t to the W minus 1. So this map, the key thing is that it is degree insensitive. It doesn't care about what the degree of GR and HR is.
But this map, this MF, the dimension is bounded by the degree. So how would you get a lower bound?
Sorry?
The dimension of F.
Because IJ vary up to degree, you are saying. Yeah, so it's a big matrix. It's an arbitrarily large matrix.
I'm saying the opposite. It seems a very small matrix because the dimension is, because there's only two variables, there's the number of possible monomials in one variable.
If the degree is very small, you can get better results. So W is the general upper bound that holds no matter what the degree.
In this particular regime, you are looking at W being much smaller than D.
I see.
So it's not only linear.
Yeah.
D can be, as I said, arbitrary means exponential.
Oh, I see.
Doubly exponential, triply exponential, whatever, we don't care. Yeah, so this, I should say that this map Rohit came up with, I have no idea how, but you will see that it magically works. Sorry? It's a typo. Yeah, so this will be a good map in the sense that if you put this, substitute this into f, then if f was non-zero, it will remain non-zero. Okay, and as you can see, it depends. So there were two parameters here potentially: width w of the matrices and the degree of the variables. Okay, x1, x2. But this map depends on only one parameter, that is the width. And magically, if f was non-zero, f of this thing is also non-zero. We will assume zero characteristic. Okay, that is one weakness which we have no idea how to correct this. So the proof is, once I tell you this, it is not very difficult. So now what you basically look at the action of phi on these coefficient operators. Okay, so the monomial x1 to the I, x2 to the j, this is mapped to this thing. Okay, this is obvious. So basically, I'm looking at this as t to the w times 1 plus t inverse, and this will be raised to the second exponent, that is j, and w times I plus j goes with the t outside. So yeah, if you look at the coefficient operator, then the first property is that I plus j, this corresponds to essentially all these diagonals, okay, various diagonals, and after a point they may be zero. So you look at the largest diagonal which still survives for this current f. Okay, so let k equal to I plus j be the largest diagonal that contributes in this coefficient matrix. And observe that that can be at most w. Okay, because the matrix has a rank upper bound of w, so in the largest diagonal there simply cannot be more entries than w, because that is exactly what gives you lower bounds the rank. Okay, so there are w many, at most that many entries in the largest diagonal corresponding to k. And so now your new polynomial is f prime. It is simply the image of the original polynomial f under phi. Okay, and look at the leading contributions from these images. Okay, so we are still keeping the monomials intact. So the monomials, these x bar, e bars, and each monomial you look at its image, and you only consider the contributions that come from this k, I plus j equal to k. Basically, this I plus j equal to k. Look at those monomials where I plus j is equal to k. Their images under phi. Okay, so they all look like this. The key thing is that this part is constant for them. Right, for all those ij's, t to the wk is the same. So the thing which is important is this 1 plus t inverse to the j, because that is exactly what is varying in the leading contributions. But obviously there are also lower monomials, and those lower monomials also give you these t monomials after the image, so they may interfere with this part. So can we control that? And that indeed gets controlled. So because the lower contributions, they will give you something just under k, right? So at most k minus 1. So this part will be something 1 plus t inverse to the j, but the important thing is that this part will be t to the wk minus 1. Now note that this is an inverse. So the maximum contributions that you get from the lower part is determined by t to the wk minus w. So there you have now a gap between wk minus w to wk. Okay, and this is the gap which will save us. So this is the gap which can only come from the leading contributions. So look at the monomials from just above wk minus w, so plus 1 all the way to t to the wk. They only come from the images of the leading monomials. And so how many are they? Well, they are at most w many. And you also know that the largest diagonals, so these monomials, leading monomials, they are at most w many. And you can already expect that these contributions, they will be linearly independent. Okay, so formally what you have to prove is that if you look at the coefficient of these monomials in the expansion of 1 plus t inverse for distinct exponents, doesn't matter what are these exponents, we just use that they are distinct and they are w many. And if you look at the, let us say, the top part, this top part of this binomial expansion, that part is linearly independent. Okay, that you can show. This is just a Vandermonde type argument, properties of Vandermonde matrix, because the binomial expansion will give you this j choose I, and you are looking at a matrix of this type. And this is where we need zero characteristic. Otherwise, this Vandermonde argument, I mean, it is false. Yeah, so just to show that these binomial vectors, they are linearly independent. And yeah, so now is it clear that phi preserves the non-zeroness of f? Right. So basically it is just because of the leading part, okay, with respect to monomial ordering that phi gives. Okay, so yeah, we have shown, we have a new hitting set, or actually a map, a very simple looking map for bivariate ROABP that doesn't depend on the individual degrees. Okay, and this is exactly what will help to complete the recursion, take us all the way to n variables. So yeah, so note that phi is obviously degree insensitive. So what we can do now is we can reduce n variables to n by 2 variables. So the idea is simply pair x1 with x2, x3 with x4, xn minus 1 to xn, and apply the map, but on x1, x2 you apply it with t1, x3, x4, t2, and xn minus 1, xn, t and half. Okay, so this way you will reduce n variables to n by 2 variables. So now you have reduced f0 to this polynomial f1, f sub 1, which has essentially the same ROABP with the a1, a2 multiplied, a3, a4 multiplied, and these are again univariates. So what has changed here is the width is still the same, but the degree grows, right? Because you multiply x1 with x2, x1 part with x2 parts, the degree grows. And so individual degree will grow w times, and width won't change. So ultimately, yeah, so there will be at most log n iterations in this recursion. So degree, individual degree, if it was you started with d, then it will get multiplied by w to the log n. Okay, and you can see that that is just n to the log w. So if w is constant, it hasn't changed by much at the end of the recursion.
So you're preserving non-zeroness in every pair,
Mm-hmm.
but why is that preserve non-zeroness?
Yeah, so you look at the function, put the other variables in the function field. I mean, no, why is it a matrix? So see, this is a, this part, so let's do this for x1, x2. So for x1, x2 part, this is a row, and the remaining thing is a column, but in disjoint variables. So that column entries you see as present in the function field. They are constants. and you are applying the map phi 1 that is on T1, image will be in T1. So the previous argument holds here as well. This is just a polynomial over the function field. And you can do this also in the middle. So x3, x4 also has the same property, because you can put x1, all the other variables in the function field. Any other questions? So this shows you the how to reduce the variables from n to 1, and the cost is that a degree will grow, but it doesn't grow by much if the width is small. Okay, so ultimately what you get is that there is a polynomial in n to the log w, d times n to the log w time hitting set for ROABPs, assuming, so we assumed here we needed the order of the variables. Okay, we assumed that the order is x1 to xn. So in general, once we will need the information how are the variables ordered. Okay, because we need them to be adjacent. If x1, x2 are far apart, then this hitting set may not work. I mean, at least we don't have a proof. We want them to be adjacent. And the characteristic 0 thing is a technical problem. So for this model, previously poly time hitting sets were not known. Okay, and even otherwise, this type of a result was not known, n to the quasi poly, but with respect to the width. Any questions?
Sorry, could you say some more about what happens if these are far apart?
When x1, x2 are far apart, when they are not adjacent.
You can't apply those lemmas, right? I mean, the information between x1 and x2, it's not necessarily not a W anymore. So it's
if you just look at the proof, in the second round you don't get an ROABP, because x1, x2 both are replaced by variable t1, and now the variable t1s are far apart, and in between you will have variable t2, t3.
I see. But so is it the non-zeroness or what is this?
So ROABP structure is lost after one round.
That is the simplest explanation, that here you don't get f sub 1. You don't get an ROABP. But at a higher level, the problem is that if your polynomial has an ROABP in one order, let's say x1 to xn, in the generic sense, there is no ROABP in other orders, at least no small ROABP in other orders. So the other result which we have is for how much time do you have? 5 minutes. Okay, so commutative ROABP is an interesting special case where the matrix product commutes. Okay, so essentially it is a polynomial f which has an ROABP with respect to any order, moreover the same ROABP. Okay. And small, obviously. So the same with W ROABP is there. W is supposed to be polynomial in n. This model is interesting mainly because this diagonal depth 3 reduction to ROABPs comes out to be a commutative ROABP. In fact, it's even stronger. What happens in this duality reduction is that all these A1 to AN, they are the same. Okay, it's even more than commutative ROABP.
Is that something very different from a symmetric function that
No. So it is certainly symmetric if all AIs were the same. But if they are different, then there is no reason. So diagonal depth 3 model is not inherently symmetric.
And then why are the AIs the same if you have a linear form with different constants? X1 and X2 have different constants.
You mean in the duality lemma?
I understand that, like, if you have a linear form and all the constants are 1, then you get the matrices which are the same. But you have to put constants in there somewhere. It's going to change your matrix. It's going to change your matrices.
They have the same form but different form.
Oh, yeah, I think you have to maybe take, apply a simple transformation on x1.
Yeah.
I think you have to multiply x1 by a vector. But the outer, so these bigger AIs, they are the same. Yeah, more or less the same. I mean, no, they are the same. It's just that before x1 you have to scale x1 in every coordinate by a different constant. That's all you have to do. Yeah, that it's exactly right. Okay. Okay, so what was known due to FSS for diagonal depth 3, that is the best hitting set, is n to the log n. Okay, that was the best. So it is even better than quasi-poly. It is n to the log n. That was known for diagonal depth 3. What we do in this work is that we combine the known techniques to actually show a similar sized hitting set for any commutative ROABP. Okay, and this is a really stronger result than just the one for diagonal depth 3, because commutative ROABPs have, they are more relaxed. I think I'll skip this proof since this is really just combining AGKS with FSS hash function. I'll quickly skip this and go directly to, okay, so what was the result? Yeah, this is we get this result, that there is a WDN raised to log W time hitting set for width W degree D commutative ROABP. That is what we get. So this extends essentially the diagonal circuit FSS result using their hash function and some special properties of the AGKS map or AGKS result on ROABP. Okay, let's skip this. So I'll just move on to conjectures which are completely combinatorial, and if you prove them, then you will have a polytime hitting set for ROABP. Okay. So next question is how could we ever improve the commutative ROABP? So yeah, let's focus on to be just for simplicity on the commutative ROABP case where the order is not important. But what I will say can also be extended to general ROABPs. So how can we improve it? And anyways, this is so close to polytime, right? This is n raised to log, so it is dangerously close to polytime. So how can we get polytime, really polytime? Well, it seems that we have to get rid of the recursive nature of the proof. Okay, so find a non-recursive argument. So here is one conjecture. So what I need is what I call an m comma w implicit hash function. Okay, so what is that? This is again a monomial ordering phi, such that so what we are doing is, let us for simplicity consider multilinear monomials. Okay, so this is essentially your space 2 to the n. You have a multilinear monomial here, and you have this MW implicit hash map, which maps it to a much smaller space. So ultimately it should be polynomial in everything. So NW, whatever, NWD, if D is arbitrary. Here we assume just D1. So it is clear that for any T to the K here, the pre-image will usually be exponentially large. Right? So it's a very large pre-image. Many things will clash under phi because you are mapping exponential space to polynomial space. But so what I want is a property of large subsets of any pre-image. Okay, so by large I would mean greater than m. So if I take any m or bigger subset m in the pre-image of any k, then there should be a subset restriction of this m which has a large image. Okay, so by subset restriction I mean that every monomial in m you restrict to only the monomials that appear in S and drop the other monomials. Okay, so when you do that, so let's say you picked a large enough subset here, M. So when you restrict it, then you will get something of roughly equal size here, M sub S. And now you again apply, again look at its image, okay, and hope that this image is, so previously it was 1, but after the restriction and again applying F, it grows to W or more. Okay, this is what I want. So pre-image, restriction, image grows the image slightly. Okay, grows it to W. So if you can find such a map phi, then you solve commutative ROABP in polytime heating set.
So you want a way of identifying every monomial with a weight?
Yeah, so phi will map every monomial to a single monomial, so a univariate monomial. Now phi should have the property that in any pre-image, if you take a large enough subset, then there should be some subset restriction. So there should exist some S which has to depend on this M, which M you took. So depending on M, there is a subset restriction such that the subset restriction's image is large. So you have, I mean, it is not very crazy because you have here exponentially many choices for S. Okay, subsets are many, but also for every M you have exponentially many choices. You can restrict in all these ways. And now what is the chance that all the images are very small? Right, that is the hope. Yeah, so the conjecture explicitly is there exists, and obviously we'll want efficient explicit. There exists MW implicit hash function phi with everything polynomial in the input size. Okay, so W, D, N are given to you in the input, and M depends on you, so that will depend on your combinatorial proof. So let's say you take M to be W, D, N square. Okay, so if that big subsets you consider in the pre-image, then there should always be a subset restriction whose image is bigger than W. I mean, it is not a very big demand. And remember that, yeah, so in general, individual degree will be some D, so you have D degree invariate monomials here. And phi is mapping them to univariate monomials. This phi being a monomial ordering currently is important for me. I cannot deal with, don't have a similar conjecture for general maps phi. This monomial ordering appears in the proof. I don't think I can give the proof. Let's skip this. So basically, with my student Rishabh, we have this result that if you have such a phi, then you have polytime heating set for commutative ROABP. This also extends to ROABPs. Conjecture has to be modified slightly. And the other thing is, yeah, you can ask the question whether probabilistic choice of phi will work. Or you can also ask the question whether a simple counting argument will rule out the existence of phi. So that the other case is not possible because Rishabh has given constructions. He has made partial progress towards the conjecture, so he has given constructions of phi that are quasi-polybig. Okay, the weights are n to the log. or n to the O tilde log. This can also be seen as an alternate proof, alternate hitting set for commutative ROABP. And so there are non-trivial constructions. They are not yet poly-sized, but it is highly non-trivial because you only need quasi-poly big weights. And yeah, the proof is probabilistic argument using Nissan-Wigderson design. Okay, so this I will skip. Maybe some of you already see the proof. So I'll just conclude. Yeah, so we solved the case of constant width ROABP. And the key open question is, can such degree-insensitive maps be designed in other situations? Okay, this bivariate ROABP was one model. But which other bivariate models you can design degree-insensitive map? So once you can design a degree-insensitive map for any model, well, the recursive structure is similar. Will give you a quasi-poly. You just have to understand bivariates. And we gave hitting sets for commutative ROABP, almost polytime, but not so. And this, yeah, so design efficient MW implicit hash.